So today we have the presentation about n jobs in three machine sequencing. So we'll start with the introduction. A sequencing is the order in which the jobs are processed. Sequence problems arise when we are concerned with situations where there is a choice in which a number of tasks can be performed. A sequencing problem could involve point one job is a manufacturing job in a manufacturing plant, aircraft waiting for landing and clearance, maintenance scheduling in a factory, programs to be run on a computer, customers in a bank, or so on. Terms used: job. What is job? Job is the job or items or customers or orders that are primary stimulus for sequencing. There should be a certain number of jobs, say n, to be processed or sequenced. Number of machines. A machine is characterized by certain processing capability or facilities through which a job must pass before it is completed in the shop. It may not be necessarily a mechanical device. Even human being assigned jobs may be taken as machines. There must be certain number of machines, say k, to be used for processing the jobs. Processing time. Every operation requires certain time to each of the machine. If the time is certain, then the determination of schedule is easy. When the processing times are uncertain, then the schedule is complex. Total elapsed time. It is the time between starting the first job and completing the last one. Idle time is the time the machine remains idle during the total elapsed time. Technological order. Different jobs may have different technological orders. It refers to the order in which various machines are required to for completing the jobs. Now, for example, here we have the diagram of start to finish, and it consists of mainly four machines: M1, M2, M3, M4. It's shown in this figure. Today we are going to discuss about just three machines. Types of first we will discuss about types of sequencing problems. There are many types of problems, such as problem with n jobs through one machine, two machine, three machine. Here's the objective: to find out the optimum sequence of jobs to be processed and starting and finishing time of various jobs through all the machines. No passing rule. This is the rule that implies passing is not allowed. That is, the same order of job is maintained over each machine. If each of the n jobs is to be processed through m machines in order, like given below: M1, M2, M3, M4, then this rule will mean that each job will go to machine M1 first, then M2, and lastly to M4 after M3. Static arrival pattern: if all the jobs are arrived simultaneously. Dynamic arrival pattern, where the jobs arrive continuously. Basic assumptions made here are: no machine can process more than one job at a time. The processing times on different machines are independent of the order in which they are processed. The time involved in the moving a job from one machine to another is negligibly small. Each job once started on a machine is to be performed up to completion on that machine. All machines are of different types. All jobs are completely known and are ready for processing. A job is processed as soon as possible, but only in the order specified. These assumptions are basically considered to make the sequencing problem a simple, otherwise complicacy may arise. Processing. Now we'll discuss about the processing n jobs on three machines as the subject. So here let there be n jobs, which each of which is processed through three machines, say A, B, and C. We'll take A, B, and C in order. No passing of jobs is permitted, and actual processing time in all three machines is known. The problem again is to find the optimum sequencing which minimizes the tree. So here the in the chart we can see job 1, 2, 3, I, and N, as we have taken it, are given here. Machine A has is been denoted by A1, A2. Likewise, all the machines till C are denoted in the same way. Now here no general solution is available at the present of such a case. However, a previous method given by Johnson can be applied in the following two conditions. There are two conditions given by Johnson. The minimum of the times for different jobs on machine A is at least equal to the maximum of the times of different jobs on machine B. Condition 2 is that the minimum of the times for different jobs on machine C is at least equal to the maximum of the times of different jobs in machine B. That is, we have to find the minimum of AI, minimum of CI, maximum of BI, and check if AI is greater than BI and or CI is greater than BI. If the above two are not satisfied, the method fails, otherwise we can proceed. So the method says that replace the given problem with an equal problem involving n jobs. Two machines, here two machines fictitiously says G and H and defines the corresponding processing time, that is GI and HI, as follows. So GI is equal to, it is taken as AI and plus BI, and HI is equal to BI plus CI. Thus for the job 1, G1 is equal to A1 plus B1, H1 is equal to B1 plus C1 from the given above mentions. Just, for the job 2, G2 is equal to A2 plus B2 and H2 is equal to B2 plus C2. The numbers get vary as per the jobs given. Now apply the same procedure and find out the optimum sequence, which shall also be optimal for the original problem. So, for example, a question is given: a machine operator has to perform three operations, turning, threading, and knurling on three machines, A, B, and C in order ABC. Find the optimum sequence when the time is given. So, here we have the job given. We have three machines, A, B, and C1, and their every machine's readings are given down below. So in the solution, minimum of AI is equal to 2 is greater than max of BI 8 is not satisfied. Minimum of CI is equal to 8 greater than max of BI is equal to 8 satisfied. Since one of the condition are satisfied, the above problem can be converted into n jobs and two machines. So the above job, taking this table, we are putting the values here and getting the values of GI and HI for every job. After that, examining the column GI and HI, we find the smallest time is 8 of job 4 and G. From here, we can find out that smallest time is 8 from job number 4. And the next smallest is 9 of job number 3 on machine G. So from here, we can see that 9 is the lowest from machine G and job number 3. Scheduled job as next to 4, also delete 3. After assigning 4 and 3, we see that there are equal minimum values. Processing time of 11 minus minutes under job 1 on G and job 5 on H. According to the rule, job 1 is scheduled next to the 3 while job 5 is assigned last as shown in the below. Job 5 from here is always assigned in the last column here, and 1 is assigned after 3. Now jobs 2 and 6 are left. The smallest value is 12 for job 6 on machine G. So we assign job 6 after 1 and we get the optimum sequence as so we can here what we are doing is job 2 and 6 are left here. The smallest value 12 is taken from this and it is assigned over here, and the optimum sequence is given as 4316 according to the given example. So total elapsed time for the original problem is we can write it as shown in the table below, and the ideal time of threading and knurling is also given out here. This is how in and out of all the three jobs are given here on three machines, and its ideal time required to do those jobs is always listed by the operator over right side in the ideal time. So thus the minimum elapsed time is 77 minutes. We can see that the elapsed time here minimum is 77 minutes. Ideal time for turning is equal to 35. It is the formula to create that 35 into bracket 77 minus 42. Ideal time for threading is, we should add all the threading times given in this column right side. So we can add these and we'll get the ideal time for threading, and knurling time we got is 8, which will be given here. If there is more knurling time, then it should be added as well. Sir, end.